So during the transfer electrolysis, you could have transferred. Now, so of course, I don't know whether any criticism of this because I haven't heard any. So I presume that people either don't want to comment on it or accept as a reasonable fact. The next, in our work, we concentrated on tritium production. And again, I'll show you typical results, what one can see. In this upper one, you see evolution of tritium on film smooth electrodes. That means electrodes which were co-deposited, but at very low current densities. It was saturated with deuterium to start with, but at much below the limiting current. You can see clearly that there is a production in I think second or third day, and then we didn't see anything until toward the end when we terminated. It was quite high. You can see also that the tritium was detected in the liquid phase, not in the gas phase. If you try to match to find out what was the rate of production, with this region here, the rate of production based on 24 hours between sampling was about 10 to the 4th atoms per second, and in this region here was somewhat higher, I think about 10 to the 4th, I think. Now, in this slide, you have another example. This is a tritium evolution found in gas phase immediately during the co-deposition experiment, where the electrode surface looked like the one having the large number of globules. Here, the rate of production is much higher, several orders of magnitude. It's about 10 to the 8th. Now, again, this technique was used by Hotko and Bakris shortly after they visited our laboratory, and they have reported in Journal of Electroanalytical Chemistry somewhat similar results to what you see here. And question reproducibility arises. Well, 6 out of 6 in their experiment, which seems to be quite good. Now, one word of caution. When we are dealing with the analysis of tritium, one has to be very careful to try to minimize errors as much as possible. First, we have to look at our setup. You have here the electrode the arrangement is given here, in which you have copper tubing covered first with silver and then coated with palladium on it, and tightly bound coil representing the platinum counter electrode. The gases were recombined on catalyst, and its value measured here. So what we have a number of checks that we haven't lost anything, that the volume corresponds to what we should have expected. Here we have the profile. You can see what we have done. We have first sampling, and then we measure the concentration, and then we added the corresponding amount, so we'll get to the initial volume, and we sampled it again to get the new starting point. We estimated that the error here, the major error, was in the measurements of T concentration rather than in any other part like current or whatever that's to be measured. Now, with these three aspects of our work, we started to think, well, how to interpret that and why the co-deposited films appear to be more reproducible than the solid rods. And one of the things which I think comes to mind is the morphology of the surface. Of course, the second one is that we saturate the electrode almost instantly. Remember that in normal procedure, the one accepted generally, the charging time is far shorter than the time needed to initiate to see the effect. And in addition to, here some 6 or 8 years ago indicated that 1 out of 4 electrodes. Again, today probably the situation is different, which I am not so sure that I don't know. In order to try to interpret that, we are trying to understand that and not getting involved in any of the nuclear physics. I'm looking at it strictly from the point of the standard electrochemistry, and in my interpretation of my trying to understand, I'm defining a region which I'll call interface region, and is modeled after the early work of Professor von Rysselberg, I think in 1961 or something at that time, in which in a number of consecutive reactions you formulate a layer in which the driving force is operating. And what do we see here? Well, on charging, we have the total current, cell current, is split into current, into 2 currents. One is the Follmer path, and the other one would be the Herowski path. This one charges, this one discharges, discharge, double path discharging. Now the absorbed hydrogen or deuterium as an atom is transferred to the lattice still as a neutral species and undergoes some sort of a ionization, that means splits into the plus and the minus, and by diffusion. Now, and the discharging reverse takes place. Now the question is again, how does it leave the, what are the processes involved between how this D plus, does it really come to the neutral, and is it essentially the reversal of this plot? Well, I really don't know. But in any event, it seems to me that there is a region in which is primarily responsible for the initiation of the effect. Now, when we are charging, or rather carrying these experiments, the current densities are quite high, and there is a gas evolution. This gas evolution produces essentially additional problems because it is responsible for locally changing the conditions. The forming gas bubble blocks the transport current. That creates local gratings, all sorts of things. And just to show you what one could expect, I'll try to illustrate that by a very simple procedure. We have created, well, we annealed a palladium in such a way that we had a large single crystal phase, that, well, not single, but the large grain, and we can see that that was looked at the surface under very low current density with Nomarsky optics, and we can see that the entrance of deuterium or hydrogen into the bulk metal is not uniform. Again, it appears that it comes in at some pre-selected spots. How that pre-selection takes place, I really don't know. Now, the next, of course, interesting problem would be what happens in the electrolyte phase. Now, when you look at the interface and this, from the solution side with some sort of interferometer attachment to your microscope, you can see that there is a change in the liquid phase. You see various gradients. These gradients are most likely associated with changes in concentration, local concentration, which of course would result from the reaction and absorption. It might also indicate thermal gradients, which I really don't know which ones they would be. But at a very small current density, you can see changes in both phases. Now, when you increase to produce hydrogen above gas bubbles, that thing will be substantially magnified, and you might expect a production of a large gradient. And this production of large gradients brings to question the formation of various instabilities, the formation of perhaps domains. This problem I do not understand, I pretend to understand, but I'm trying to devise experiments now that would lead me to somewhat better understanding of the behavior of the interface during the process, and perhaps that way try to contribute something to the better understanding of the conditions leading to the initiation phenomenon. To conclude, in our work, we have concentrated primarily on the so-called nuclear ash in the form of X-rays and in form of tritium production. And I must add to it that calorimetry, by its, you cannot really measure if one would wish to measure X-rays and, for example, current, it would be very difficult because the X-ray intensity is very, very low. You have to bring your detector very close to your radiation source. Of course, the calorimetry and tritium probably can be done quite easy. Well, we haven't done that, so this essentially is what we have done during the time that I was actively involved in this research. Thank you.
The floor is open for discussion.
Could you describe your cathode a little bit more? I saw copper, silver, palladium. What's the cathode originally made of? Before,
Which one?
Before the deposition.
Oh, that was a copper, mostly copper, and then we put a flash silver on top of it.
What's the purpose of the silver?
It is better binding between the palladium and the film adheres slightly better.
Since you mentioned film adherence, like do you have a lot of problems with the films bubbling off or blowing off, blistering?
Pardon?
Do the films, once they're plated on, tend to blister off as they're loaded, or do they?
Yes, well, that depends how you prepare it. If you prepare it so there is a rather extended the dendritic type, then of course during the gas evolution you will have some loosening of the production of some sort of loose particles in the electrolyte.
The other question is, could you tell us the current density that you use during co-deposition? You said it's very low, but...
Well, what we have done really, we control potential rather than current. So we start with some potential and increase it gradually. And we can, you remember that when you're absorbing hydrogen, you don't necessarily see its evolution. So you will see absorption long before the evolution.
So you keep the current density low enough that you see no bevel evolution?
That's right, yes. And then, of course, when you carry it out...
Potential is high enough to make sure you're forming hydrogen.
Yes.
I want to make a comment, really, to stop something disappearing from you. In 1989, someone wrote to me from Belgium to say that he had put into a cell a powder doped scintillator. Unfortunately, I cannot remember what it was. It might have been fluoride or it might have been lithium fluoride. And he said he saw scintillation from the region of the cathode. Now, it might be that that would be a very good way of looking for X-rays, because we could also have energy dispersion. And I kept on meaning to do it, or draw attention to this work, and I have been able to do so. I just want to draw attention to it here in case somebody should have the means of executing the experiment.
I can reinforce that, and I'm aware of this result, and we many times thought of doing it. The problem with working in strong basic electrolytes is you digest your scintillator, so you need to encapsulate or choose a different electrolyte.
I rather think this man used some other electrolyte.
Yes.
But I think it would be such a neat way of doing it. In fact, I had even thought of doing the whole experiment with a perdurated scintillator.
This is one of Tom Passel's favorite undone experiments.
We all have a long list of undone experiments.
I think I will terminate discussion here, and thank you for getting us a little bit back on time, Dr. Szpak. The next paper will be presented by Professor Dash, talking about titanium, slight change of topic.
So this work is an update on the titanium system, which we started working on a few years ago. And the work is by, how's this work? Maybe it doesn't work.
It's non-intuitive.
I got it.
No, other way around, I think. No.
Okay, so this is the work of John Warner, who's a graduate student at Portland State in the physics department. He has completed his master's degree on this work and is continuing towards the doctorate degree. And we are fortunate to have funding from the Drexler Foundation, from the New York Community Trust, and it's hard to get money for this work from the federal government, but not impossible.
Now it is.
So this is what we reported a few years ago, the master's degree of Radovan Kopacek. D stands for deuterium, heavy water cell, and C for a control cell using light water. So what he found was that he could get a higher temperature from the heavy water cell after the order of minutes, even though the power input was about half a watt less. So simple calorimetry says that he has at least a half a watt excess heat here. So the question is, how reproducible is this? And that's what we have attempted to find out. So we work with a setup like this. We have 8 cells, 7 electrolytic, and the 8th one is ambient temperature monitored. So what we did in this experiment is we have duplicate cells as closely the same as we could make them. And what we're doing is we're varying the width of the electrode so that we have a difference in current density on pairs of cells. So these two have the same current density, these two have the same, these two have the same. This is a control. Cells 1 to 6 have platinum electrodes, and cell 7 has, platinum, they all have platinum anodes. Cell 7 has platinum cathode and light water, and all the rest have titanium cathodes and heavy water. Okay, so then hooked up to a power supply and data acquisition system. Okay, so this is what it looks like. So the 8 cells I spoke of are embedded in styrofoam, power supplies, multimeter, and computer data acquisition system. What does the cell look like? Okay, so we have the cathode, which is sealed off with heat shrinkable Teflon. The anode, made of platinum in all cases, some electrolyte. This is a double-walled cell. In the outer wall is a temperature sensor. In the upper part of the cell is a recombination catalyst. So these are closed cells. We have a septum, so we don't make a bomb here. If the catalyst didn't work, the septum would give and release the pressure. So the way we calculate whether or not we have any excess heat in this is we wait till we have a steady state, and then in the control cell, the power input is equal to the rate of heat loss times the temperature gradient between the cell and the ambient. So we can solve this for the rate of heat loss, which we call R, and then apply that R to the experimental cell, which if we have a greater temperature gradient between the cell and ambient, then we have excess heat, which we can calculate. So this works if we don't lose any mass during the experiment. If we lose mass, then we have to correct for that. So it's best that if we don't lose any mass. Okay, now, so in this experiment, we have excess heat from some of the cells and not from others. Okay, here's a cell where the cathode width was about 2 millimeters, giving a current density, very high current density, almost 2 amps per centimeter squared. Runtime 115 hours. What happens is usually failure occurs at the interface between the Teflon and the lower titanium cathode. So in this experiment, we had excess heat of this magnitude, where the 0.09 watts is 3 sigma. So this is statistically significant. And then what we do is we characterize the cathodes before and after the experiment. So in this characterization, we came up with sulfur, potassium, calcium, vanadium, chromium, iron, nickel, and copper that were not there. We didn't find those before the experiment. Okay, so here's some of the data. So what we have is temperature, time, and for the control cell, the temperature is represented with triangles, and for the experimental cell with pluses. So we're maintaining about a 5-degree C temperature difference between the two during the steady state period, where the input power is the same within a few milliwatts. So if you make the calculation, a known chemical reaction is to produce TiD2, which for our titanium cathode weighing 11 milligrams would give 22 joules. But during 25-hour steady state period for this experiment, we get 19,000 joules excess heat, a difference of almost 3 orders of magnitude. So in our characterization, that's the cathode before electrolysis, same cathode after electrolysis. Maybe the most evident difference is the bottom edge. This is the bottom edge of the original, the bottom edge after electrolysis. There's some erosion. I don't understand why titanium cathode erodes, but that's what happens. And up in this area, there's something different. So this is what we looked at. So this is done with a scanning electron microscope with an attached energy dispersive spectrometer. So magnifying this area, over here we have areas 1 and 2 where, let's see, okay, area 1 shows these elements. In addition to titanium, a big iron peak, chromium, potassium, and sulfur. And the only element amongst these that we are sure of that's present ahead of time is sulfur. So what we think is that sulfur comes from the electrolyte, and it occurs in hot spots. Okay, so then we did ultrasonic cleaning, and now this area A is magnified over here, and we have analyses from points 1 and 2, and again we confirm these elements, and the other area gives only titanium. Okay, so still a higher magnification. Maybe you can see things a little better. One is a little bright thing sticking up here, which doesn't come off from ultrasonic cleaning, so it's pretty well attached. And it gives it gives these peaks. In addition to titanium, big chromium peak, big iron peak, big nickel peak. Whereas the place right next to it, 2, which looks dark in this picture, only titanium. Okay, so cell 4 in this experiment was supposed to be exactly the same. As well as we could make it. But it gave no excess heat and no new elements. So what we've been doing recently is we've been using a different technique of chemical analysis, neutron activation analysis, which we do at Reed College, Portland, Oregon. So I give them electrodes and they analyze them blind. They don't know what I'm giving them. And what we found was cell 3 gave 28 parts per million, plus or minus 12 parts per million. This is the cell that produced excess heat. Cell 4, no excess heat, no chromium. And also in the experiment, they put in a blank, which also gave no chromium. So the other elements that we picked up were not easy to detect by neutron activation analysis. So this looks promising. One result doesn't make it real, but we're encouraged to keep going on it. Here's another set of results from that experiment. Okay, so we have cells 5 and 6, which again were supposed to be the same. Cathodes about 5 millimeters wide. Current density much less than the other set I talked about. What happened on both of these is the cathode totally disintegrated. We ended up with a slurry of particles in the cell in both of them. Okay, 6 had excess heat, and 5, nothing. As far as the composition of the cathode, we have this slurry. We've tried some analysis on it, but don't know how to interpret the results yet. Okay, now, as I said, the titanium erodes in this experiment. So we only saw this once, but it gives you an idea what I'm talking about. The original surface looks like this. So in this electrode, this patch was passive. And all the rest of it was active and eroded. So we very seldom, in fact, I only remember seeing this once, but that's what the original surface would look like. Now, I mentioned the idea of hotspots, which Stan Szpak has shown very nicely. So here's what we think are hot spots on titanium. There's 3. This one's hard to see, I guess. this, and this look very similar. And the interpretation is the bright part sticks up and gives more emission in the electron microscope. The dark part sticks down. So there are bumps on the surface surrounded by valleys. So we analyze this patch and then get outside the bump and analyze this patch. And then for the third one, same thing. And this is what we get. The area outside the patch gives pure titanium. The bump, the three bumps give about 5% iron and 2 or 3% chromium. Just a trace of nickel. So years ago, we reported hot spots in palladium. So here's what we think a hot spot in palladium looks like. We published this. This is atomic force microscope work. So it looks like this with radial lines. Our interpretation is this spot melted, exuded some material, and then recrystallized. So with this instrument, you can measure the depth. And so anyway, in titanium, in palladium, we seem to get explosions on the surface which exude material, and the spots I showed for titanium look a bit different. Okay, so we did this 6-cell experiment and had 2 out of 6 excess heat production. So how can we enhance that? Well, there's evidence in the literature that catalysts improve by shock loading. So by shock loading, you introduce defects such as dislocations and point defects into the material. Well, we tried a different way to introduce defects called rolling. So we did another experiment, 8-cell experiment, and got these results. So with 20% deformation, both cells, identical cells, gave this excess heat at the level of 0.4 watts. With 35%, both gave excess heat, but they didn't fall on each other. With 50% cold reduction, one gave no excess heat and the other one gave excess heat. And the error bars corresponded to 3 sigma. The first experiment was done at no deformation, 2 out of 6. This one, 5 out of 6, we have excess heat. So maybe there's some optimum in the low amount of deformation area. That's the case for shock loading of catalysts as well. If we go beyond 50%, we get no excess heat. So we're also trying to improve our calorimetry, and at the suggestion of Van Bush, we got into CPEC envelope calorimetry. So in this calorimeter, we have calibrated, and our result is that we have an accuracy of plus or minus 22 milliwatts. We've done 2 experiments so far, no excess heat in the first one and 100 milliwatts in the second one, but we're still learning how to optimize this experiment. So this is what it looks like. Calorimeter, constant temperature bath to keep the outer wall of the calorimeter at constant temperature. Power supply, computerized data acquisition system. So even if we don't get excess heat, we still can detect unexpected elements sometimes. Okay, so all these bright patches here, showing up here, and here's one that looks like it grew out of the electrode. All these patches give unexpected elements, whereas over here, this area, which we also analyzed, gave only pure titanium. So in these particles, chromium is the major peak. Chromium far exceeds the iron peak here. And so we have sulfur is detected, chromium and iron. Okay. What is the origin of these unexpected elements which we observe? Are they pre-existing inclusions? Well, we buy the best titanium we can find. It's supposed to be 4 nines, and we check it ahead of time. And if we detect anything other than titanium, we don't use it. Anyway, we don't think these are pre-existing conclusions because, for example, in that last photo I showed, these would be extended in the rolling direction if they were. Solid state diffusion. So if you have impurities which are insoluble in titanium deuteride, maybe they diffuse out. But at less than 100 degrees centigrade, where we operate, we don't think this is viable. Electrodeposition of impurities. Okay. The most abundant impurities that we have are sulfur, platinum from the anode or from the recombination catalyst, and Al2O3. Okay, we seldom see Al2O3 or platinum. Sulfur is often detected in trace amounts along with other unexpected elements. So we think at a hot spot, the electrolyte interacts with the hot spot, producing a sulfur compound in that area. Okay, and then the radical idea of transmutation. If you somehow have thermal neutrons available, transmutation would be possible. So I don't know how many of you have read Kozima's book, but that's the thesis of his book, that we have thermal neutrons available in these experiments. Okay, so takes a lot of work to be absolutely sure where these things are coming from. Maybe start by refining the original material to make sure that it's not there when you start. So, finally, our conclusions. We can get excess heat from electrolysis of heavy water with titanium. It appears to be, the reproducibility appears to be enhanced by a small amount of cold deformation before the experiment. And bulk analysis, mass spectrometer, and now NAA shows that there are possibly changes that might be connected with a nuclear process. So we think that our results are consistent with the occurrence of a nuclear reaction during electrolysis of heavy water with titanium. Thank you for listening.
John, this paper's open for discussion. So,
Well, you know, Deborah Rawlinson did work with palladium. One thing she found was the purity concentrated on quite large factors during the course of electrolysis. Could this be playing a role with the impurities that appear on the surface?
Enhanced electrodiffusion. Yeah, there's definitely enhanced electrodiffusion occurring, but why do you form these? Why don't you form these uniformly? I don't know whether she found localized concentrations like we do.
I don't think she said that.
there's one other thing which you've probably considered in terms of solid-state diffusion. It's true that solid-state diffusion from the bulk is going to be very, very slow at the temperatures that you operate at, but this process is greatly enhanced by the presence of hydrogen or deuterium. So you can stimulate the removal of elements from metal matrix with the presence of hydrogen. So you need to, I assume you've considered that in your analysis.
Well, we have to be sure about our original material than we are right now. That's for sure. You know, if you want to make the world believe something as radical as this, you've got to be damn sure.
But neutron activation analysis before and afterwards would help you with respect to chromium anyway.
Yeah, well, we had one electrode, two electrodes cut side by side from the same piece of metal. One gave it, one didn't.
Before and afterwards, same one. Thank you very much. The final paper of this morning's session is going to be presented by Professor Bush, and I believe some theoretical consideration. Thank you.
Actually, we have three short papers, and I think since we're running a little slow here, what I'll do is I'll give the first two papers and get us to lunch, and then later on at the end of the session, around 3:34, give the third talk. But let me give an advertisement for that talk. It's in here. Let's see. Okay. So can cold fusion be explained in terms of phonon laser? If I'm posing that question, your guess is probably that I'm going to argue that it is a sort of phonon laser. So if we don't have time to give that talk now, we'll give it later. Okay. title of the talk. And I am Dr. Bush. I have a co-author, Mark McGovern, who is a senior in Cal Poly in physics. Mark happens to be in the audience here. People have asked me about having undergraduates in the physics group, and my observation to them is always that it seems like the less physics you have, the better you do in cold fusion. That's just a casual observation. Okay. This is kind of a solemn group, so I want to go back to the halcyon days, the beginning of cold fusion, when it appeared that it was just a juggernaut, and these are some of the cartoons that came along at that time. So you can see Eureka, upon hearing the news, nuclear physicists responded variously. Cold fusion in a test tube in Utah, discovered by chemists? This has got to be a bad dream. It can't be so easy. This will make us look stupid. Our grant money gone. So much for scientific objectivity. Okay, just a couple more here to wake people up. Fusion fever sweeps the scientific community. Extra, conflicting reports pour in from labs all over the world. Meanwhile, at the facilities where difficult and expensive fusion research used to take place. So, I guess everybody knows that hot fusion is being gradually shut down in this country because people have seen that it has no possibility. Now, just one more along those lines. This is from the New Yorker. Whoops, it's back here. Thank you. And she's saying, don't you remember we were at Herb and Sally's, and Herb said he knew how to achieve fusion at room temperature using only gin and vermouth. Now, as far as a lot of the controversy on cold fusion, I think it can be summed up by a statement from Tolstoy. For those of you who know the classics here, this is a little fuzzy, I'm sorry. And it says, I know that most men, including those at ease with problems of the greatest complexity, can seldom accept even the simplest and most obvious truth if it be such as would oblige them to admit the falsity of conclusions which they have delighted and explained to colleagues, which they have proudly taught to others, and which they have woven thread by thread into the fabric of their life. That really says it all. I'm grateful to Joe Ignat for that. By the way, I am a teacher, as you've gathered, and so there'll be a quiz at the end, so pay close attention. I've got 3 different talks up here. I don't want to get these mixed up. So this is the first talk. So, title is Theoretical Considerations for Cold Fusion Based Upon Co-Production of Heated Tritium. And you can see down here from the abstract that we're going to use data of Bakras, Kunamatsu, and Makubri, and employ these distinguish between rival possibilities for statistical mechanical models for heated tritium production in cold fusion, or if you will, anomalous phenomena in deuterated metals. Okay? And I say that the best agreement is attained for a 2-dimensional approach to heat production and a 1-dimensional approach to tritium production. And we'll look at the consequences also of that. Okay. Here's the data, and I should really borrow somebody else's slide. This is the Makubri SRI data, and you had a previous slide on this that was much better. This is a little worn. I'm kind of sorry about that. Apologies to, yeah, he's got it.
Everyone uses that slide.
Okay, but you can see here that we've got excess power in watts versus the loading fraction here, and you can see that this is very dramatic. And so what we did to help with a model was to take that mass of points and extract kind of averages, average data points. So you can see here is the first Makubri data point, and this is in fact the model prediction for that. So this model is not too bad here. Where did this model come from? Well, primarily it was based on statistical mechanics, and you can see these little chains with the x's where you have an x that's an interstitial site occupied by a deuteron. And so the idea is the production of helium-4, and of course the attendant heat, is that you've got a number of nearest neighbors. And I actually refer to that as the lattice-assisted anti-tokamak regime. Okay? And now, over and against that, you have tritium production. You notice in the case of tritium production, or neutron production, the neutron production is related by a branching ratio, that you have isolated neighbors. So here you have these two, but you have a vacant site here and a vacant site here. So statistical mechanics are quite different. Here is the final formula for this. What's happening here? I see a little static electricity. So here's the overall formula that comes out of this. Now, you can see the statistical mechanical factor involving the filling fraction S, the stoichiometry. This complicated thing here, it is complicated. You can see this S, the filling also comes into this power of 10. And this is S raised to the minus 112th power. Yes, minus 112th power.
Are you going to cover this on the quiz?
Yeah, not that particular feature, so don't worry about it.
Maybe we quiz you.
We've got the tritium slide, so we made one up for the tritium statistical mechanical factor. And you can see this is, has a few features that you would expect. For example, when S is 0, you would expect any tritium production. Also, when S is 1, based on my model of having isolated pairs, you shouldn't expect anything either. Okay. Well, let's see how the model fits McCoubrey data, which I guess I'm a little biased. Maybe it's American bias, but I tend to think that the SRI, McCoubrey's SRI data is maybe the best we have going. What we've done here is looked at the one-dimensional model, the two-dimensional model, and the three-dimensional model. Now, these, whether it's one-dimensional, two-dimensional, three-dimensional, depends on whether this thing, or the comparable thing for the helium production, is like this for the one-dimensional. If this is squared, that's a two-dimensional. If it's cubed, that's a three-dimensional. Just to give you an idea there. But now look at the data, and you can see here we're fitting to his 1.30 watt excess power point, and that's why these all agree across the board here. The one-dimensional gives an average deviation of 0.17 for that, the two-dimensional 0.04, the three-dimensional 0.09. Down here, the one-dimensional is 0.15, for the 2D it's 0.05, for the 3D it's 0.08. And if you continue this, you'll see that the one-dimensional always does much worse than the other two. And the other two really compete fairly well with each other. So here's the lower portion of McCoubrey's data where we fit it. So this is the 0.08 data point. Again, that's why these three results here agree. And now the three-dimensional tends to do a little better than the two-dimensional. The one-dimensional clearly is, and also ran if you go down this, well, maybe not too bad though. This is 0.14, 0.12, 0.09, 0.10, 0.08, 0.05. 0.09, 0.06, 0.03, and actually you can see here that the 3D is doing a little better than the 2D, and they're both doing better than the 1D. Now on the Kunamatsu data, I think we could just dispense with that. I'll just tell you what happens there. Once again, the two-dimensional and three-dimensional are fairly competitive. The one-dimensional model just falls to the wayside there. Well, where do we bring in the data of Bacchus? I'm sorry John isn't at this conference, and I know many of you wish that he could be. So he's in retirement. Bacchus at an EPRI meeting early in the halcyon days of cold fusion mentioned a datum that they had at Texas A&M whereby the heat production associated with the tritium that they were getting was 1/1000th of what you'd expect for heat production on the basis of helium-4. So the idea now is to take the two models that have survived the McCoubrey data, which is the two-dimensional, three-dimensional, and look at these matched up with the different dimensional tritium models and see which one satisfies the Bacchus criterion of of a ratio of 1,000 for the heat to the tritium heat. And here you see we've got the two-dimensional heat model. Here is the two-dimensional tritium model. And you can see that this ratio of 1,000 is achieved at about an S of 0.72. Problem with that is that that's usually way lower than you would see excess heat. So this seems improbable. Okay. Let's take a look at this one. And let's see how many permutations are there. Okay, so this now shows you H1, H2, and H3. This is a one-dimensional heat model, the two-dimensional and the three-dimensional, and we're comparing those with the one-dimensional tritium model. And you can see that there are only two that can make it. This again is rule out, the S is too small, okay? But for a ratio of 1,000, the H2 and the T1 intersect here at 0.82, so that's a good possibility. But maybe 0.92, except we've ruled out the H1. So we've already ruled out the H1. We can rule out the H3 for this. So you see the only one that really survives is the H2. And the question is it T1, T2, or T3? Let's take a look at that. Okay, well, here is the H2 that we've chosen, and here is the T1, and you can see that fits real well. That gives us 0.82. How about the others? How do they fit? Where the heck are they? Okay, so this slide's been scattered somewhere here. Okay, I'm going to have to find that slide a little later, but basically what it shows is that as you go from T1 to T2 to T3 with the H2, comparing them, that the S values really point right to the T1 model. So it seems like the heat based on this model is a two-dimensional effect. It's a surface effect, whereas the tritium production, the one-dimensional chain works quite well. Now, what are the consequences of this? Let's just take a look at that. Okay. Well, the ramifications of this, let's see, okay. Somebody mentioned that we would need a lot of palladium to make possible reactors if a reactor turns out to be conceivable, but in fact, I would argue just the other, based on this result. If the H2 result is correct, then in fact the excess heat production is surface production, and you wouldn't want to go out and buy palladium futures or stock up on palladium because the amount of palladium you could put on your thumb would spread over a large enough surface area to give you a reactor, say, for the city of LA. Okay, now Dr. Eagle and I did an experiment on thin films, and that work tends to support the two-dimensional stuff. That was a 5-micron film of palladium that was electroplated to a silver substrate. And I might just mention that Los Alamos, Dr. Storms was the one who helped us with this project, and he and we are still interested in doing more thin film work. Okay,